let's now see how to apply the theorem we just proved in the previous video to some practical questions. So consider the following problem. Let P be a point on the hyperbolic plane. So here's a hyperbolic plane. So here will be the x-axis, x, y. Okay, and the point has coordinates 5, 12. So let's say this is 5, 5, 10, 12. So the point lies somewhere here, that's P. And consider about geodesic. So geodesic through P centered at 0. Okay, so that's going to be a circle centered at 0. That goes like this. I think it should be, that's fine. The point P should be a little further left. Okay. So 5 here. Okay, so that's the geodesic gamma 1. Now I want to construct a different geodesic, gamma 2, that also goes through this point and forms the angle of 60 degrees with this one. So some gamma 2 so it goes through the point P, and I want this angle here to be 60 degrees. Okay, so this geodesic is centered somewhere. I think it's going to be centered, I think because I know the solution, it's going to be centered a little bit outside of, so I think it's going to be centered somewhere here. I mean, it doesn't really matter, but let C2 be the center of gamma 2. So let C2 be the center of gamma 2. So C2 is given by some coordinate, some x coordinate alpha, and then 0 on the y axis. So it's alpha, 0. Okay, so we want to find that alpha. Once we have alpha, because we have also the coordinates of P, we will know the radius of that circle. So we will know its center and the radius, so we will know everything. So we want to find the alpha. Okay, so this is C2. Where is C1? Where is the center of the geodesic, of the red geodesic? Well, that's the origin. C1 is right here. So we can now look at the triangle from C1 to P, and then oops, down. It should go down to C2. Okay, so we can look at this triangle. So this will be C1, P, C2. And so we know by the previous proposition, by the theorem we proved in the previous video, so we know by our theorem that, well, we're looking at the angle between two bowed geodesics. So the angle between gamma 1 and gamma 2 is actually the same as the angle between C1, of the angle C1 PC2. It's that angle actually that is also 60 degrees. That's, if you look at the previous proposition, I keep saying proposition, previous theorem. That's what makes that theorem quite useful, is because it translates these angles between curves into something very something we're very familiar with, namely angles in triangles. So that means this angle is 60 degrees. Okay, so this is 60 degrees. So we're trying to find this point C2, right? So I want to find alpha. What else do I know? Well, if I look at this angle here, which I denote maybe in purple, let's call this angle beta. So I know that the tangent of beta, because the vertex here is at the origin, the tangent is just the coordinates, can be read off the coordinates of the point P. So it's 12 over 5, right? The tangent is this leg divided by that leg, but this leg is 12 and that leg is 5. From which I can read off beta as arctangent of 12 over 5, and if anyone is interested, that's roughly 67.38 degrees. Which gives me that the last angle, let's call this, well, gamma maybe not a good letter now, so let's call the last angle a delta. So this tells me that delta is, well, this is a Euclidean triangle, right? So the sum of the angles is 180. So if this one is 67.38, that one is 60, so delta will be 52.62. 52.62 degrees. Yeah. Okay. So how do I get alpha? Now I'm just going to use the law of sines. Law of sines in a Euclidean triangle. After all, this is the Euclidean triangle. So by the law of sines, it tells me, well, that if I take sine 60 and divide it by this length, which is alpha, then I get the same as sine delta divided by this length, the length C1p. Okay, but sine delta, that is equal to, so sine delta is sine of 52.62 degrees. And what's C1p? Well, that's just from Pythagorean theorem. That's the radius of that red circle. So it's 5 squared plus 12 squared. Square root of that will give you 13. So from this you will see that alpha is equal roughly 13.9. Okay, so now you have this point. So you have the center of the circle of the other geodesy. And now you can compute the radius as well, because you know the coordinates of P and you know the coordinates of C2. Okay, let's look at another application. Namely, finding angles in hyperbolic triangles. And we're going to do a particularly simple triangle to see, to make sort of the calculation somewhat easier. So question 2, find the angles in the hyperbolic triangle whose vertices are A equals 0, 1, B equals 2, 1, and C equals 4, 1. So you see, from the Euclidean point of view, they all lie on the same line, namely y equals 1. But on the hyperbolic plane, they actually form a triangle. So here's a hyperbolic plane. So 1, 1, 2, 1, 2, 3, 4. So the points are here. A, B should be on the same level. B and C. So how does the hyperbolic triangle look like? Well, I have to find the geodesic between these 2 points, but look. going to be about geodesics because the points are not on top of each other. So it's going to be a circle centered somewhere on the x-axis that goes to both of these points. But I know it has to be centered at 1, so its distance from this point is the same as the distance from that point, so it's going to be a circle like that. Similarly between these two, okay. And finally, the last one has to be the circle that is centered here between, that's centered on the x-axis and goes through the most extreme points. So that's going to be something like that. Okay, so this is your triangle. This is point A, B, and C. Let's denote these points maybe by, also let's give them some names, maybe P, R, and Q. Okay, so I have several geodesics here, right? If you wish, this could be gamma 1, gamma 2, and gamma 3. So let's find the angles in this triangle. So first of all, the angle between gamma 1 and gamma 3 is the same as the angle between gamma 2 and gamma 3. So the angle between, so I can write it as AB, AC, which is of course the same as the angle between gamma 1 and gamma 3, is actually the same as the angle between gamma 2 and gamma 3. So the same as the angle between AC and BC. Okay, these two angles are the same. What is this angle? Well, so let's just concentrate on the angle between AB and AC. So by our theorem, so the last equality is by the theorem from the previous video. That's the angle PAR. So the angle PAR. So this angle here, which maybe I'm just going to denote in blue, is the same as the angle PAR, same as this angle. Okay, and how do we compute the angle PAR? Well, we can just use the law of cosines from the plane. So this is equal to, so this is law of cosines. For triangle APR. So that will give us what? So that will give us, how does law of cosines work? If I want to get cosine of this, sorry, I shouldn't write, yeah, okay. So if I want to get this angle, so that's arc cosine of, all right, so cosine of this angle, if I want to compute that, that's this length squared plus this length squared minus this length squared divided by twice these two lengths. So that's AP squared plus AR squared minus, I shouldn't be pointing to this length, it's this triangle APR. So minus this length squared, PR squared, divided by 2 AP AR. Right? Again, the law of cosines on the plane just tells you that AP squared plus AR squared minus PR squared is equal to 2 AP AR times cosine of this angle. So if I want to get this angle, you just do that. So what is this? This is arc cosine of AP is, this is 1, 1, so that's going to be radical 2, so that's 2 plus AR, 1, 2, so that's 5. PR, that distance is 1, divided by 2 radical 2 radical 5. And if you use a calculator, that's approximately 18.4 degrees. Okay, so these two angles are actually 18.4. So it's this one. So what remains to be found is the last angle, namely this one over here. Okay, so for the angle between AB and BC, which is the angle between the geodesics gamma 1 and gamma 2, we again use the theorem. And now this is the last case of the theorem. So that angle will be equal to pi minus the angle PBQ. Okay, so it's pi minus this angle here. So this angle and that angle are supplementary. PBQ. Okay, so what is this? Well, again, we just use the law of cosines. So the law of cosines on the plane, right? So it's pi minus arc cosine of PBQ. Okay, so I want this angle, so it's PB squared plus BQ squared minus PQ squared divided by 2 BQ. So that's pi minus arc cosine of PB squared. Again, 1 and 1, so that's actually radical 2, so that's 2. Plus, this is also 2, minus what's PQ? PQ is 2, so PQ squared is 4. Okay, so it doesn't matter what the denominator is, this is just arc cosine of 0. So it's pi minus pi halves. So it's pi halves. Alright, I seem to be very inconsistent using degrees and radians. So this angle is actually 90 degrees. Okay, and we found all the angles in this triangle. Something to note, the sum of the angles is actually, so note, the sum of the angles in the triangle ABC is less than 180 degrees, which is, as you will see, typical of hyperbolic triangles.